Hello, and welcome to our AP review of topic 5.6, reaction energy profile. I've already talked about reaction energy profiles in a lot of videos, even prior to this one, but I'll be more specific about what a reaction energy profile is in this video. So, a reaction energy profile is simply a way of representing the complex energy changes in a chemical reaction in a graphical form. And so let's take a look at what that means. So reaction energy profile is simply a graph. So it's going to have an x and a y axis. On the y axis, you have the potential energy of the substances involved in the chemical reaction. And on the x axis, you have the reaction coordinate. In some other videos, I might have called this the reaction progress. That's the same thing. It's just the reaction going from reactants to products. Potential energy relates to the energy stored in the bonds of a chemical reaction. And so we're going to start with the energy, the relative energy of the reactants. They're going to be at some level on this potential energy. So I'm just going to, for this particular reaction energy profile, I'm going to write the energy of the reactants up here at the top. The reactants are always on the left side of the reaction coordinate. Then, as the reaction progresses, you are going to have to break some bonds typically. And breaking bonds is an endothermic process. So we're going to go up in potential energy because it requires energy to be absorbed to break bonds. Then new bonds are going to form. And so energy is going to go down because anytime bonds are formed, energy goes down. In this particular reaction, we're going to look at an exothermic reaction, meaning that the products have lower potential energy in their bonds than the reactants. So let's label what everything means in here. So we have reactants that we started with. So reactants are always on the left side. Products are always going to be on the right side of the reaction coordinate. From the energy difference between the reactants and the products is going to be our enthalpy change for this reaction. So I'm going to draw a dotted line just to show where the energy is of our products. The energy difference from the reactants to the products is our enthalpy change. And if you recall, enthalpy is the energy involved in the heat change and the work. If we do this reaction at constant pressure, then the enthalpy change is simply the heat released in this reaction. Notice that we're going down in energy from reactants to products. So this is an exothermic reaction because we lost enthalpy. So this enthalpy change for this reaction is going to be negative. You'll also notice that we had to go up in energy before we could get down to the products. This change from the reactants to the top of this hump up here is called the activation energy. And that's the energy required to break the bonds in the reactants to form a transition state. That transition state or activated complex can then react and form the products in this chemical reaction. Now, this is for an elementary reaction. Notice there is only one hump here. And so an elementary reaction only has one activation energy, one transition state, and no intermediates. And so we do not have multiple activation energies because this is an elementary reaction, meaning that there's only one activation energy. And this is for an exothermic reaction. What is this going to look like for an endothermic reaction? Well, we're going to have the exact same type of coordinate where we're going to have the potential energy on the y-axis. We're going to have the reaction coordinate on the x-axis. And this time, the reactants are going to have lower energy than our products. And so our products are going to end up being somewhere up here relative to our reactants. We're still going to require energy to be put in to break bonds. And then when new bonds are formed, the energy is going to go down, but this time not as far down as the reactant started because this is an overall endothermic reaction. So our reactants are over here again on the left-hand side. Our products are on the right-hand side. The difference between the reactants and the products energy is our enthalpy change. So notice this time the enthalpy is going up. So delta H is going to be a positive for this reaction. So this is an endothermic reaction, and we're going to have a positive delta H for this reaction. This is endothermic. The difference between the energy of the reactants up to the activated complex or transition state is going to be the activation energy. So all of this is the activation energy. Notice it's a very large activation energy because this is an endothermic reaction. So we have to put a lot of energy in order to get it to the products on the right-hand side. So this is our reaction energy profile for an elementary reaction, for an exothermic reaction, and endothermic reaction. If you have a multi-step reaction, non-elementary step reaction, then you're going to have multiple activation energies. And another video will show that. One thing I do want to point out is that the rate of the reaction depends on this activation energy. So how large is this activation energy? That's going to affect the rate of the reaction. So the smaller the activation energy, the faster the reaction can be. Also, the rate is temperature dependent. If you increase the average kinetic energy of your reactants particles, then they have more kinetic energy that allows them to get over this hump more easily, over this activation energy more easily. There is a quantitative way of calculating or relating the kinetic energy, the temperature of the particles, to the rate, and that's called the Arrhenius equation. The Arrhenius equation is the rate constant equals a proportionality constant times E to the negative activation energy over RT. Now, you do not have to do any calculations with the Arrhenius equation on the AP test, and so I am not going to go into any type of great detail about this equation. All this equation does is says if you have a higher temperature, then that's going to increase the rate of the reaction. And you can study this equation. You need to make sure you notice the negative in the equation. But you can study this equation and look that if you indeed increase temperature in this equation, that you will increase the rate of the reaction. Again, there's no calculations using the Arrhenius equation, so you just need to qualitatively know increasing temperature will increase the rate of the reaction because more molecules can get over the activation energy. So that's a brief introduction or review of the reaction energy profile. If you have any questions, you're always welcome to ask me questions and I'll be happy to help you out. Good luck in your studies. Bye-bye.